Part 1, Vectors. We introduce two vectors, A and B, so we can practice magnitude, dot product, cross product, lines and planes. Let vector A equal the ordered triple 1, 2, 2. Let vector B equal the ordered triple 2, negative 1, 2. To find the magnitude of a vector, we take the square root of the sum of the squares of its components. For vector A, that means the magnitude of A equals the square root of 1 squared plus 2 squared plus 2 squared. 1 squared is 1, 2 squared is 4, and 2 squared is 4 again, so we get the square root of 1 plus 4 plus 4. 1 plus 4 plus 4 equals 9, so the magnitude of A equals the square root of 9, which equals 3. To find a unit vector, we divide each component of A by its magnitude, which is 3. So the unit vector in the direction of A is 1/3, 2/3, 2/3. To find the dot product of two vectors, we multiply matching components together and add the results. For a dot B, that is 1 times 2 plus 2 times negative 1 plus 2 times 2. 1 times 2 is 2, 2 times negative 1 is negative 2, and 2 times 2 is 4, so we have 2 minus 2 plus 4. 2 minus 2 plus 4 equals 4, so a dot B equals 4. To find the angle between two vectors, we use cosine of theta equals the dot product, divided by the product of their magnitudes. The magnitude of B works out the same way as before, the square root of 4 plus 1 plus 4, which is the square root of 9, which is 3. So cosine of theta equals 4 divided by 3 times 3, which is 4 over 9. This confirms the angle between A and B using the value. Cosine of theta equals 4/9. To find the cross product of two vectors, we use the determinant pattern with I hat, j hat, and k hat across the top row. Working through that determinant pattern for a cross B gives us the vector 6, 2, negative 5. As a check, the cross product must be perpendicular to A, so we test this with a dot product. Taking 6, 2, negative 5, dotted with 1, 2, 2 gives 6 plus 4 plus negative 10. 6 plus 4 is 10, and 10 plus negative 10 is 0, so the cross product is confirmed perpendicular to A. Now we use vector B as a direction to write the line through the point 1, 2, 2. This line is written as position equals 1, 2, 2 plus t times 2, negative 1, 2. Next we write the plane through that same point, using the cross product 6, 2, negative 5 as its normal vector. The plane equation becomes 6x plus 2y minus 5z equals 0. Let's picture this geometry in 2 dimensions first, as a flat cross section showing the line and the plane's edge meeting at our point. Now watch that same picture rotate into 3 dimensions, where the flat plane tilts through space and the line pierces through it at exactly the point 1, 2, 2. As a check, we plug the point back into the plane equation, 6 times 1 plus 2 times 2 minus 5 times 2, which is 6 plus 4 minus 10 equals 0, so the point does lie on the plane. Finally, we take this plane equation together with 2 further plane equations and solve all 3 simultaneously using determinants to locate the single point where all 3 planes meet. Part 2. Partial differentiation. We now work with a function of 2 variables to explore gradients and rates of change. Let f of x, y equal x squared times y plus y cubed minus 3x. The partial derivative with respect to x means we treat y as a constant and differentiate as normal with respect to x. Differentiating term by term, x squared y gives 2xy, y cubed gives 0, and negative 3x gives negative 3. So the partial derivative of f with respect to x equals 2xy minus 3. The partial derivative with respect to y means we now treat x as a constant and differentiate with respect to y. Differentiating term by term, x squared y gives x squared, y cubed gives 3y squared, and negative 3x gives 0. So the partial derivative of f with respect to y equals x squared plus 3y squared. Now we evaluate both partial derivatives at the point 1, 1. The partial derivative with respect to x becomes 2 times 1 minus 3, which is 2 minus 3 equals negative 1. The partial derivative with respect to y becomes 1 squared plus 3 times 1 squared, which is 1 plus 3 equals 4. So the gradient of f at the point 1, 1 is the vector negative 1, 4. To find a directional derivative, we take the dot product of the gradient with a given unit vector. Using the direction 3/5, 4/5, we compute -1 times 3/5 plus 4 times 4/5. -1 times 3/5 is -3/5, and 4 times 4/5 is 16/5, and adding these gives 13/5. So the directional derivative at this point in this direction equals 13/5. Now suppose x equals t squared and y equals t, and we want the rate of change of f with respect to t using the chain rule. The chain rule says df by dt equals partial f by partial x times dx by dt plus partial f by partial y times dy by dt. At t equals 1, x equals 1 and y equals 1, so we reuse our earlier partial derivatives, -1 and 4. The derivative of x with respect to t is 2t, which at t equals 1 is 2, and the derivative of y with respect to t is simply 1. Putting it together, df by dt equals -1 times 2 plus 4 times 1, which is -2 plus 4 equals 2. So the rate of change of f with respect to t at t equals 1 equals 2. Now let's introduce a second function, g of x, y equal x squared plus y squared minus 4x minus 6y plus 5. To find a critical point, we set both partial derivatives of g equal to 0. The partial derivative with respect to x is 2x minus 4, and setting this to 0 gives x equals 2. The partial derivative with respect to y is 2y minus 6, and setting this to 0 gives y equals 3. So the critical point of g is at 2, 3. To confirm what kind of critical point this is, we use the Hessian test built from the second partial derivatives. The second partial derivative with respect to x twice is 2, the second partial derivative with respect to y twice is also 2, and the mixed partial derivative is 0. The Hessian determinant equals 2 times 2 minus 0 squared, which is 4 minus 0 equals 4. Since this Hessian determinant is positive and the second partial derivative with respect to x twice is also positive, the critical point is confirmed as a local minimum. Now let's minimize x squared plus y squared, subject to the constraint x plus y equals 10, using Lagrange multipliers. The method says the gradient of the function we are minimizing must equal lambda times the gradient of the constraint. The gradient of x squared plus y squared is 2x 2y, and the gradient of the constraint x plus y is 1, 1. Setting these proportional gives 2x equals lambda and 2y equals lambda, so x must equal y. Combining x equals y with the constraint x plus y equals 10 gives 2x equals 10, so x equals 5, and therefore y equals 5 too. As a check, we substitute back into the original function 5 squared plus 5 squared, which is 25 plus 25 equals 50. So the minimum value of x squared plus y squared, subject to that constraint, is 50, occurring at the point 5, 5. Part 3, multiple integration. We now extend these ideas into double and triple integrals. Let's evaluate the double integral of x plus y over a rectangle where x runs from 0 to 3 and y runs from 0 to 2. We first picture this rectangle as a flat two-dimensional region, and then imagine the surface, x plus y, rising above it in 3 dimensions like a tilted roof. We integrate first with respect to y, holding x constant, so the inner integral is integral from 0 to 2 of x plus y dy. That inner integral evaluates to x times y plus 1/2 y squared, evaluated from 0 to 2, which gives 2x plus 2. Now we integrate this result with respect to x from 0 to 3, so we need integral from 0 to 3 of 2x plus 2 dx. That evaluates to x squared plus 2x, evaluated from 0 to 3, which gives 9 plus 6 equals 15. As a check, this matches the volume we would see under that tilted roof shape sitting above the rectangle, confirming 15 is correct. Next, let's find the volume under a paraboloid, given by z equals 4 minus x squared minus y squared over a disk of radius 2. Picture this first as a flat circle in 2 dimensions, the disk of radius 2, and then watch it lift into 3 dimensions as a dome-shaped surface curving down to 0 at the edge. Because the region is circular, we switch to polar coordinates, where x equals r cosine theta, y equals r sine theta, and the small area element becomes r d theta. In polar form, the volume integral becomes integral from 0 to 2 pi integral from 0 to 2 of 4 minus r squared times r dr d theta. The inner integral over r is integral from 0 to 2 of 4r minus r cubed dr, which evaluates to 2r squared minus 1/4 r to the 4, evaluated from 0 to 2. Plugging in r equals 2 gives 2 times 4 minus 1/4 times 16, which is 8 minus 4, equals 4. Now we integrate this constant result, 4 over theta from 0 to 2 pi, giving 4 times 2 pi equals 8 pi. As a check, this 8 pi matches the expected dome-shaped volume sitting above the disk of radius 2, so our answer is confirmed. Now let's evaluate a triple integral of x times y times z over the unit cube, where x, y, and z each run from 0 to 1. Because the integrand factors neatly, this triple integral splits into 3 separate one-dimensional integrals multiplied together. Each one is integral from 0 to 1 of x dx, which evaluates to 1/2, and the same result holds for y and for z. Multiplying these together, 1/2 times 1/2 times 1/2 gives 1/8. As a check, since the cube is symmetric in x, y, and z, it makes sense that all 3 factors are identical, confirming 1/8 is correct. Finally, let's use cylindrical coordinates to confirm the volume of a cylinder with radius 2 and height 3. Picture the cylinder first as a flat circle of radius 2 in 2 dimensions, then watch it extrude upward into 3 dimensions to height 3. In cylindrical coordinates, the volume integral becomes integral from 0 to 3, integral from 0 to 2 pi, integral from 0 to 2 of r dr d theta dz. The inner integral over r gives 1/2 r squared evaluated from 0 to 2, which is 1/2 times 4 equals 2. Integrating that over theta from 0 to 2 pi gives 2 times 2 pi equals 4 pi. Integrating that over z from 0 to 3 gives 4 pi times 3 equals 12 pi. As a check, this matches the standard formula for the volume of a cylinder, pi times radius squared times height, which is pi times 4 times 3, also 12 pi. Part 4, Vector Calculus. We finish by exploring a wind field using line integrals, divergence, curl, and 2 major theorems. Let the wind field f equal the vector negative y x 0. First, picture this field in 2 dimensions as arrows swirling counterclockwise around the origin, then lift that same picture into 3 dimensions as a flat swirling sheet of arrows in the xy plane. Let's find the line integral of this field around a circle of radius 2 using the parametrization x equals 2 cosine theta, y equals 2 sine theta. Along this path, the field becomes negative 2 sin theta, 2 cosine theta, 0, and we combine this with the small displacement vector dx, dy. Working through the standard result for this kind of rotational field around a circle of radius r gives 2 pi times r squared. Substituting r equals 2 gives 2 pi times 4 equals 8 pi. So the line integral of the wind field around this circle equals 8 pi. Now let's confirm this using Green's theorem, which says the line integral around a closed curve equals the double integral of the curl over the region it encloses. In 2 dimensions, the curl of this field equals the partial derivative of x with respect to x minus the partial derivative of negative y with respect to y, which is 1 minus negative 1 equals 2. The double integral of this constant curl, 2 over the disk of radius 2, equals 2 times the area of the disk. The area of a disk of radius 2 is pi times 2 squared, which is 4 pi, so 2 times 4 pi equals 8 pi. As a check, this 8 pi from Green's theorem exactly matches the 8 pi we found directly from the line integral. Now let's find the full 3-dimensional divergence of this wind field. Divergence adds up the partial derivative of each component with respect to its matching variable, giving partial of negative y with respect to x, plus partial of x with respect to y, plus partial of 0 with respect to z. Each of these 3 terms is 0, so the divergence of the wind field equals 0 everywhere. The full 3-dimensional curl of this field works out to be the vector 0, 0, 2, matching the value 2 we found in our 2-dimensional curl calculation. Next, let's use the divergence theorem to find the flux of a different field, the vector x, y, z, flowing out of a sphere of radius 2. Picture this sphere first as a flat circle outline in 2 dimensions, then inflate that same outline into a full 3-dimensional sphere. The divergence theorem says the flux out of a closed surface equals the triple integral of the divergence over the solid region inside. The divergence of the vector field x, y, z is 1 plus 1 plus 1, which equals 3. So the flux equals 3 times the volume of the sphere. The volume of a sphere of radius 2 is 4/3 pi times 2 cubed, which is 4/3 pi times 8, equals 32/3 pi. Multiplying by 3, the flux equals 3 times 32/3 pi, which equals 32 pi. As a check, this 32 pi is exactly the flux we expect for this simple expanding field passing through a sphere of radius 2. Finally, let's confirm Stokes' theorem, which says the circulation of a field around a closed curve equals the surface integral of its curl over any surface bounded by that curve. We already found the circulation of the wind field around our circle of radius 2 to be 8 pi. We also already found that the surface integral of the curl over the flat disk that circle encloses equals 8 pi. Since both values equal 8 pi, this confirms Stokes' theorem for our wind field, completing our full worked journey through vectors, partial differentiation, multiple integration, and vector calculus.